In this video, we're going to look at some more common uses for oxidizers, including a really fun one involving fireworks and other kinds of controlled explosive kinds of reactions and controlled combustion reactions. But before we get to that, let's talk about chlorine dioxide. Now, chlorine dioxide is another chlorine-based component substance, and in it we see that we have a highly unstable gas. Why is it unstable? Well, if we look at its Lewis structure, what we would find is that we've got chlorine in the middle, we've got bonds to oxygen atoms on either side, and we end up running out of electrons for the chlorine to bond up and to pair up with. So we end up with an unpaired electron on that chlorine, this guy right here. And because of that, this chlorine dioxide is going to be very reactive because it's going to try to pair up that unpaired electron dot with something else. And so it's going to go out and it's going to be really reactive as a result of that as it tries to stabilize the structure around that chlorine. Now, because of this lack of stability, because of this reactivity, we can see that it's going to cause pretty severe damage to your eyes, pretty severe damage to your respiratory system. As an oxidizer, it is 2.5 times more powerful than chlorine. And if you recall from our list of reagents in our last lecture, chlorine is kind of a moderate oxidizer. It's kind of on the higher to weaker side here. So chlorine dioxide fits into this zone just a little bit better than chlorine itself is. But what we use it for is as a microbiocide. So we can throw chlorine dioxide into a room. It'll kill all of the bacteria, all of the viruses, everything that's in that room that is a potential biohazard. So it's really, really effective as that because of its reactivity and because it's in the gas phase, it'll be able to spread out in the room a lot more easily. Moving on to talking about fireworks. Fireworks, we find that the chlorate family of materials, sodium chlorite, sodium chlorate, sodium perchlorate, these substances are used in fireworks production. These are your primary oxidizers in those reactions. Now, what we'll find is that fireworks are a complicated chemistry of not only these oxidizers, but a series of fuels, in particular metallic fuels, that are used to generate the different colors, the different effects that you see. So we often find, for example, magnesium. Magnesium powder is used to make the colors brighter, to enhance the brilliance. And you've seen the reaction before. Magnesium, when it reacts in the air, when it reacts under a flame, gives us that bright white color. Well, that's utilized to the maximum effect in a firework. We also see the use of aluminum flakes. Aluminum flakes are used to kind of produce that luminous tail. So when a firework gets shot up, you can see that you can see it as it goes up. That's usually aluminum that is responsible for that. And so the gradual burning of those aluminum flakes as the firework goes up into the atmosphere to explode gives that luminous tail kind of effect. Now, what we'll see for fireworks is that fireworks are all going to be labeled as explosives, and so they're all going to be DOT class 1 materials, either class 1.1, 1.2, 1.3, or 1.4. Now, looking more generically at fireworks, overall, the fuels involved are going to be carbon and sulfur. That's why fireworks have that particular smell to them. especially if a lot of them have gone off. You get that sulfury, sulfur dioxide kind of smell on the 4th of July when you go to a big fireworks display, or if you have a fireworks that you're setting off at your home. Um, Oxidizers, most of them fall into the chlorate categories. Again, um, the sodium chlorite, ClO2, the sodium chlorate, ClO3, the potassium chlorate, ClO3 again. And we saw in the last video, the Screaming Gummy Bear, the impact that chlorates have on reactions such as this. For these kinds of reactions, the reaction goes as follows. We get a decomposition, high intensity decomposition going on here, where the heat of the reaction starts to break down this into common salts, sodium chloride, and oxygen gas. And so I get 3 oxygen gas molecules for every 2 molecules of chlorate. And that oxygen gas can then go react with the carbon and the sulfur in the fuel to make carbon dioxide and sulfur dioxide. And again, that sulfur dioxide, that is what is responsible for that odor that we associate with fireworks, especially large quantities of fireworks. Now, where it gets kind of interesting is that we can incorporate some other kinds of chemistry into the mixture. So what color do we see when the firework actually explodes? Well, that depends on what other stuff's being added to it. So the carbon and the sulfur are already there. That's part of the black powder mixture that is being put up. But what we're really seeing here is, in terms of colors, think about the flame testing that you did a few weeks back in lab. Barium compounds give a green color, green flame. Lithium compounds give a red flame. Copper gives a bluish to blue-green kind of flame. Strontium gives red. Sodium gives yellow. Potassium gives violet. Calcium gives a red-orange color. If we release excess oxygen, it can make the flames feel more bluish. If we have a lack of oxygen, the flames will feel a little bit appear a little bit more yellowish. So there's a very delicate chemistry. There's a very interesting balance of reactions that are taking on there that go into the process and production of a firework, and it's really kind of interesting to watch and to look at how it's being done and how it is integrated. All the different chemistry to make the displays really cool and interesting. Another thing that we can look at are signaling flares, signaling smokes. What we see in those are very similar kinds of reactions where we've got potassium chlorate, that's going to be our primary oxidizer. We've got our elemental sulfur that is combined with bicarbonate, and together they make the fuel that is ultimately going to react. And then we throw in some dye in there to allow the smoke to um, have a color of some kind. Moving away from the things that explode and that go boom, some other kinds of potential oxidizers, perchlorates. We mentioned perchlorates as one of the possible ingredients in fireworks, although it's far less commonly used. Perchlorates have a special danger here in the United States because in a lot of places they've been identified in as part of the groundwater supply. And when you ingest perchlorates into your body, they do have a potential to damage your thyroid gland, to cause neurological problems, as well as impacting growth and development, not only for children that are, born and developing, but also for those that are still in the womb. So there are some negative effects associated with them. It's one of the reasons why we have to be really careful about them. Another thing that we can look at as far as common oxidizers are concerned, ammonium compounds. Ammonium compounds are commonly found in especially fertilizers, where we can see them used. We can also see them used as a component of certain types of explosives. We identified ammonium nitrate in a previous slide as being a uh, relatively dangerous oxidizer, especially if it gets combined with some other agents. Ammonium nitrate is a moderate oxidizer, or actually, I'm sorry, it's a weak oxidizer. But when that ammonium ion gets combined with other oxidizing ions like permanganate or chlorate, then it can actually be quite explosive, and that's where we run into those kinds of issues. We also see ammonium compounds used occasionally as anesthetics by dentists, which is an interesting kind of uh, use there. The last thing that we're going to talk about in this particular video are chromium compounds. Now, chromium compounds, in particular hexavalent chromium, chromium that is in the positive 6 oxidation state, most commonly found as the chemical formula CrO3, chromium 3 or excuse me, chromium 6 oxide. This particular form of chromium um, has a number of different uses. We see it along with its counterpart, the chromate ion, um, and its counterpart, the dichromate ion, Cr2O7, -2. These are commonly used in pigments. This is actually found, your common breathalyzer test uses chromium 6 oxide. And what's kind of cool about it is the breathalyzer test utilizes this. The alcohol in your breath gets oxidized by the chromium 6 oxide, and it causes the chromium compound to change colors, and that's what gets detected by the breathalyzer based on the rate of conversion. So how much of the original chromium 6 gets changed over, that tells you how much alcohol is in someone's breath, and that's what determines whether or not you're driving legally or illegally. Um, so potassium dichromate, this is what is commonly used in chrome plating. Formula for that is K2Cr2O7. Really strong oxidizer. Dichromates tend not to want to stay that way long, and they will even go into the chromium 6 form of chromate ion over time. They'll just decompose on their own. Chromium trioxide, as I've mentioned before, chromium anhydride, as it's sometimes known, is used for a number of different kinds of processes. Metal treatment processes, chrome plating, reacting with copper to strip it from things, anodizing aluminum, um, uh, making things that are more corrosion preventive. And as I mentioned before, the chromium trioxide um, was used at least at one point in time in breathalyzer tests for that very purpose. It's being phased out because of the dangers of inhaling chromium trioxide. But it was one of the premier ways to test for breath alcohol content up until even just a few years ago. So we're going to close this video here, and we'll conclude with one more video on oxidizers coming up next. Until then, have a good day.